You all know that a failure in embedded system could be very catastrophic. It can be annoying on your laptop, but really catastrophic on any embedded software. So there are many verification challenges in order to avoid this kind of error. And there are a lot of costs also associated to these verification activities. You may know that testing effort is huge and can represent, is generally representing half of the cost of the full project. You also know that there is a huge work on requirements that are not often fulfilling the needs. So there is work on the requirements, the cost of the bugs that is increasingly exponentially when found late, all the challenges related to late testing activities, and of course, and this is one of the most important topic for today's, that the testing execution has to adapt to a variety of hardware targets. So during this webinar and together with Matthew, we will explain how you can address those challenges. So let's start with one of the best way to save time and to address well verification challenges is really to apply a model-based approach where we will focus all the work on the left side of the V-cycle. What's very important is to focus the effort on the model level and then rely on KCG, which is our automatic code generation, which is qualified so that we can assess the code that is generated, meaning that this is removing the SIL activities, the software in the loop activities. This is one of the best way to save time. And with this saving, we can focus on the model and apply some verification at model level, and then again relying on KCG and removing SIL activities. So again, removing some activities at code level. So moving to the flow we use to present with a model-based approach, with a SCADE approach, of course, everything starts with requirements. So you have your requirements in DOORS, in JAMA, Polarion, any kind of tool like this. And then you can start designing, of course, making the design, the architecture, software architecture first. So we have SCADE architect for this. You may do your safety analysis on this, but then, and this is the real scope of the application, you may start developing the control part of the software, and we will focus on the usage of SCADE Suite today. And then with SCADE Suite, we will generate the code. This is what I've explained previously. So this code is qualified. So we apply a certified automatic code generation for this according to many standards, DO-178C, but also ISO 26262 and many other standards, and up to the most critical level, of course. And with this, and applying this approach together with SCADE Test, we can test the application on host and on target using what Rapita Verification Suite is providing, and this is what we will present and demo today. So moving to the details, I will explain, moving to all the steps of the verification very quickly, how we can cope and with the challenges. So if you can see here on the left part of the V-cycle, of course, everything starts from, well, we start from system requirements, then software requirements. Then for software requirements, there is two very big activities. First is to validate the requirement, to check the requirements are appropriate, and then to start the creation of the test cases. Then we will go step by step until the test execution on target. Let's focus now on one typical error at requirement level. So what we can do together with SCADE Test, for instance, in order to reduce the number of errors at requirements level. What we propose is a tool that enable, which is a SCADE Test Rapid Prototyper, that enable yes, the possibility to exercise and to work with early prototype. So what we recommend is, in order to validate the requirement, to do some model first, mock-up, and exercise this using a panel, a graphical panel, in order to exercise this. You will see that in the demo later on in action, but this is really a very efficient way to manage and to interact with the system with some slide bars, etc., and also some feedbacks about to check the behavior of the system. So this is one way to avoid errors at requirements level. Then we can continue. Of course, starting from requirements, you need to create your test cases. So with SCADE Tests, we provide a language. It can be both textual or using a tabular view, and this is the one we will show in the demo. And sorry, and then this language is modular. It's readable. The tabular view is very easy to understand, and so that you can easily create your test cases and review the test cases. And it provides many capabilities like invariant checkings, interval expression checkings, etc. Let's move on. So one of, again, another typical error is does the design that does not comply with requirement. This is a kind of error we want to check, and of course to check that the model you have made is really implementing the requirements you need to implement. Okay, so for this, of course, we will apply SCADE test first on host. So again, a way to perform the verification and the testing activity very early in the process, still on the left side of the V cycle. So we can run all the activities. We are using the code which is generated by KCG for this, and we generate a report, a compliance testing report, that shows all the past failed results of the testing activities. Of course, this can be run in a batch mode or in interactive mode. So then when you run this on host on your laptop, you can have this kind of result where we can compare the expected values with some actual values, applying some tolerances. And this is what we will show in the demo together with the Rapita team. And we generate this conformance report, and the tool is qualified. And this is why we provide this kind of textual report that can be shown to the authorities. Let's move on. So again, this is really the best way to check that your model is implementing the requirements. Another important activity is to check that your design does not have deactivated part, and also to check that you have made enough testing. So this is all the activities related to coverage activities, model and code coverage activities. For this, we provide in SCADE Test a model and code coverage tool that is performing this coverage analysis. Okay, and then for this, we generate, of course, a report, but also a graphical interface in order to ease all the coverage analysis work, showing what is covered, what is not covered in red, what is partially covered in orange, showing what are the missing parts of the coverage directly in the model. So again, even if it's applied at model level and code level, we show all the results at model level. So again, a good way to see and to show and to demonstrate that the software design does not have deactivated parts, and also you have made enough testing. And the last very important topic is to check that the the testing, and again, the same test case that you have made is running exactly in the same way on the target, because you know that on the target there is some differences in terms of precision, for instance. So the question is, does the target behave in a different way compared to the host? And of course, if we look at the arithmetics, etc. And this is where, of course, the usage of Rapita is very important for this. So we are dealing with many companies, and of course today we will focus on what Rapita is proposing in order to reuse exactly the same test cases on the target. And of course, Matthew and Rapita will explain that in more details. So of course, this is a good way, again, to save time and to avoid this kind of error that you have different behavior on host and on target. So I will make now a short demo. So it's a pre-recorded demo that we have made showing the full verification flow of a typical SCADE application.
In this first part of the demo, I will show how we can assess the behavior of a SCADE application. And we will take a flight control, a simplified flight control application for this. So this is the SCADE tool with a simplified flight control application with several operators dealing with alarm manager and the flight control. And we will take the operator under test and we will close the loop with a model of the plane. Just to check the behavior of this. What we will do first is that we will use the Rapid Prototyper tool in order to exercise this application. So the control panel you can see here is a way to interact with the application very easily. This is what we can do with the control panel. And also we have here integrated SCADE display application that shows the display part of the aircraft. So first with the control panel we can set some target speed, target altitude, and activate the autopilot, and then we can see the behavior. We can see the behavior of the application to check if it behaves correctly or not. So we can increase the target speed, increase the target altitude, and see if some alarms are raised or not very easily. So this is what we can do with the SCADE test Rapid Prototyper, is building this kind of interface to interact with the application under test. And this is a very good way first to check that the behavior is okay. This is not yet testing, it's debugging, it's just checking the behavior. It's also a good way to check if we have well understood the requirements also. So, and we can very easily connect this kind of panel with the SCADE application. Okay, so we can activate the role, and okay, and you can see here we can see also, of course, the SCADE application running with the debugger. Okay, so this is a first way to perform some verification, is to check the behavior very intuitively, I would say. And now we will move to the testing aspect. So I will open a SCADE test project. Of course, the SCADE test project is implementing the same requirements, and you can see on the right the requirements. And here we have made two test cases. These are made using Excel. You can see in column all the the inputs, and we can set values to the input, and we can set some expected outputs. For instance, we can set some expected throttle command, we can set some expected elevator commands, etc. So this is a way to define some test cases using SCADE Test. So now, first I will run the test case execution on host using SCADE Test. So this is done with the graphical interface of SCADE Test, and you can see here we have the result. The two test cases are passed, and we can see here the result. We can compare the actual values with the expected ones, applying of course the tolerance that we have asked, and we can check here that the behavior is okay, and yeah, okay. And in addition to this graphical representation, we have the conformance report. This report is textual. It's very important because this one is qualified. I mean, our tools are qualified, and of course you can rely on the content of this document, and this is the document that you need to show to the authorities, just to show them that you have done the conformance testing. And now we will start another activity, which is model coverage. In fact, it's model and code coverage. We will apply the MCDC criteria for this activity, and then we will rerun, of course, the same test cases, and we will measure model and code coverage. And you will see the result in a few seconds. So you can see here the results. So we can get here the result of the coverage. You can see that for each operator you have the coverage, which part is covered, is observed, which part is not covered, etc. And you can see the result on the model. So using the model, you can see immediately which part is not covered. For instance, this is not, the false value is not covered here. And again, in this transition, the false trigger is not covered. So very easily, you can see which part are fully covered. These ones are fully covered. This one is fully covered. And for some, this, for instance, one state is not activated, for instance. So this is concluding the SCADE suite and SCADE part of the demo.
Thank you very much for that, Francois. So if Matt is around, we'll pass over to Matt now for his section.
Thank you, Nick. Thank you, Francois, and hello, everyone. So Rapita Systems was founded as a spin-off from the Real-Time Systems Group at the University of York in 2005. Our HQ is based in York in the United Kingdom, but we also have an office in North America, and we work with customers through our distributors all over the world, as you can see in the diagram here. And RVS stands for Rapita Verification Suite. It's a collection of tools designed specifically for software verification on the target hardware. Our tools work primarily through code instrumentation. So we inject instrumentation points, extra code fragments, into your source code in order to measure things like timing and the results of tests. This approach means we are completely architecture independent. So if you can compile your source code in either C, C++, or Ada, if you can compile that for a particular piece of hardware, then we can use RVS with that particular piece of hardware. And we can work with model-based tools from Ansys in order to complete the loop and go all the way from the model down to the real hardware. And we can also fill in any gaps, such as a startup code or device drivers, anything like that that's not part of the model. We can also provide code coverage and testing of that source code as well. Through SCADE, you can complete all your functional testing at the model level. And because the code generator is qualified, you can also claim credit for code coverage at model level as well. So your model in the loop testing is all handled by SCADE Test. So RVS is addressing the other side, the processor in the loop and hardware in the loop testing. And what we're going to show today is that we can run these tests back to back for a really efficient overall workflow, taking you all the way from the model right the way down to the production system. So the tools we're going to focus on today are RapiTest, which is automating test execution, and RapiTime, which is going to perform execution time analysis. So RapiTest is a complete testing solution that allows you to define tests, automate them, and run them anywhere on target or on host. It's not just limited to unit testing. We can perform integration level testing, software testing, software hardware integration testing, all the way up to system test level. We focus heavily on the automation side of things because this is the way we can really deliver the value in terms of making testing easier and more efficient. For example, we can integrate with continuous integration environments, build environments. We have specific plugins for both Jenkins and Bamboo that let you view your test results and the history of test results and test trends right on the main dashboard. So you can see very quickly if you're suddenly starting to fail more tests than you used to, or if tests are passing. You can also see your timing analysis, so you can identify if a change to your source code has caused a sudden spike in the execution time. You can pick that up at an early level there. And this means you can run your tests more often and earlier in the development cycle. We aim to offer efficient test generation. By analyzing all of your source code, we can automatically fill out tests templates, if you will, which allow you to quickly add the test data and get running tests as quickly as possible. So we have many different formats you can use to input the test data to RapiTest. We support spreadsheets, scripts, and we even support external formats, which is what we're going to use today. The workflow for RapiTest is highly customizable. All the stages of the procedure can be customized, and we can inject extra actions at any point. And this makes it really easy to fit into the sort of testing environment that you happen to have. An example of this is that we can easily modify the test harness to stream test data in and out. Normally, we would compile the test vectors into the source code itself, which is the easiest way to get ultimate portability, so you can combine an executable with all the test data in it that you can run on host or target or anywhere. But sometimes, if you have very large volumes of test data, very large tables, for example, it's not appropriate to compile that in. So we have methods where we can send that data to and from the target in order to complete that sort of testing. And finally, to reduce certification risk, all of our tools come with a qualification kit for DO-178C, which will take you all the way up to the highest level of criticality for DAL-A systems. So the main use cases of RapiTest are providing verification evidence and automating it so we can complete testing through the life cycle. This sort of automation and early testing is a really proven strategy for preventing overruns in your project schedule due to surprises that occur at the end of the project. Essentially, the earlier you can catch and fix errors, the less the impact those errors will have on your overall system deployment. What we've developed in coordination with Ansys is a way to run exactly the same tests on on the model as well as on the target hardware. So we're not just running the same type of test, we're literally using the same test files, and we are able to convert these on the fly. So you don't have to change the format. RVS will read the native SCADE test formats, and then it will use them internally to build these test harnesses that you can then run on your real target hardware. So that's a big advantage, the fact that your tests remain in native SCADE format, so you don't have to do any permanent conversion. It also means you can pick up changes to the SCADE tests very quickly. The other thing that we're going to talk about today is timing analysis through RapiTime. And timing analysis is very important, but it really it's only touched on by these 3 DO-178C objectives and a similar small set of objectives in ISO 26262 for automotive. Essentially, DO-178 is saying your software has to be correct. It has to obey the time and space partitioning. So we're looking at time partitioning in this example. And it is compatible with the target computer in the sense that it will run, the code will run on the CPU that you have selected for the final hardware. So 3 very small objectives, but they represent a very difficult problem. It sounds very simple, but in reality, it's very difficult to prove to a high level of scrutiny that your system is compatible with the target computer, is going to perform within its timing deadlines. And the reason for this is that timing behavior is generally invisible to the user. You can only really see if there are very large problems with it. What's going on inside the system and how the different components interact with each other is completely invisible to the end user. So here's an example of what I mean by this. This is a real example. We were working with a customer who had a fixed round-robin schedule with a number of minor frames, 8 minor frames in every major frame. And they had one set of tasks that was supposed to run in the 3rd, 5th, and 7th minor frame, and another set of tasks that was supposed to run in the 2nd, 4th, 6th, and 8th minor frames. And these were handled by different teams. And there was a difference in understanding, shall we say, on what is the first frame. Is we calling the first frame 1, or are we calling the first frame 0? So one team assumed that the first frame is frame 0. So we're going to run, our tasks will be set to run on frame number 1, 3, 5, and 7. The other team thought that the frame started at 1. So they were going to run their tasks on frame 1, 3, 5, and 7. So what the customer intended to happen is what we can see at the bottom of the screen here. But what actually happened, because of the difference, the off by 1 error in the numbering of the frames, what was actually happening was half of the frames were completely empty and the other half contained 2 tasks each. But the system as a whole was still meeting its deadlines. Both tasks were completing within the minor frame because their CPU utilization was less than 50%. So at a glance, externally looking at the system, it seems to be running fine. But until we actually deployed RapiTime and actually looked at what was going on internally, the customer was unaware of the fact that they'd doubled up half of their frames, and by doing so, their overhead was dramatically less than what they would have expected. So timing analysis approaches have traditionally fallen into 2 camps. We've done dynamic analysis, where we run the system, we run the code on the hardware, and using either some internal method or an external method, we can directly time how long it takes to execute. The other approach is static analysis, where you use a model of the CPU which contains how long each instruction will execute for in terms of cycles. And then you can look at the object code directly and try and estimate the execution time of the code without running it on the real hardware. And both of these methods have advantages and disadvantages. Dynamic analysis, you need a big testing rig, you need the real hardware, etc. But you are getting numbers that are really representative of that hardware. The static analysis approach can be done on a host PC much earlier in the development cycle, but there's no absolute guarantee of correlation of those timing results. RapiTime, on the other hand, is a hybrid timing analysis tool. So it combines aspects of both static and dynamic analysis. So it will tell you your high watermark time, which is the term we use for the slowest observed execution time, as well as an analytical worst case time, which is the system's estimate of how slow the software could potentially be in practice. And RapiTime also automates these measurements and runs the actual code measurements on the real hardware. This is another area where we can begin our testing on the model using SCADE TSV, Timing and Stack Verifier, which is a static analysis approach, before confirming the results on the real hardware using RapiTime. And here's an example of how RapiTime actually works. If you have a look at the code on the left of the screen, what we have in the middle is a diagram that represents the control flow of that code. So there are two if-then-else statements. The numbers in each rectangle represent the execution time of each of those pieces of code, for example, in microseconds. So the first piece of code takes 10 microseconds, then the true branch takes 20 microseconds, the false branch takes 50 microseconds, etc. So you can run a test vector against this code, and it could hit both of the true branches and give us an execution time observed externally at 85 microseconds. We could then run a different test vector that hits both of the false branches and gives us an overall execution time of 110 microseconds. Now, these two test vectors would give you 100% MCDC coverage. So from a code coverage point of view, those vectors are all you need for that code fragment. However, the eagle-eye viewers might have noticed that there is a third possibility here, or third and fourth possibility, but there is a possibility here that you can go false and then true, and that could hit a complete execution time of 140 microseconds. So what RapiTime does is, instead of just taking the overall execution time for a piece of code, we record execution times for code fragments and then look to see if there's a way that these could be combined that give a longer execution time than was observed in testing. The benefits of this: firstly, it can reduce the cost involved in timing analysis simply by automating most of the gathering and collating of the results. We deliver results from the real hardware, so they are representative of the behavior of your code in the field. And we can also guide optimization efforts. So as well as showing you what the execution time is, we can break down which parts of code are contributing most of the time overhead. And this means you can guide your optimization efforts to just those parts of the code. And we can also show you what the results, so we can compare before and after on timings from before the optimization was applied and after, to make sure that your optimization effort is giving you the benefit in execution time that you're expecting. So here's an example of what can be saved, what can be achieved in practice. One of our customers reduced the time taken to perform their timing analysis from 243 days, which is 8 months, down to 1 day. This seems pretty extreme and quite a very large reduction in effort. But essentially, if you ask a developer to tell you how long a piece of code executes for, well, they can very easily add a piece of code at the start and end of every function that will record the execution time. And then you can do that for every function in your system, build a big spreadsheet of all the numbers, add the data in. And this is basically what the customer was doing, all by hand in large, enormous Excel spreadsheets. And RapiTime came in, we automated the process of gathering all these data, collating it, and produce all of the same timing data that they had after 8 months, but all within a single day. RapiTime will also focus on the worst case time. If your software is on time on average, it'll be on time most of the time. But for safety critical systems, if your worst case meets the timing deadline, then your software will be on time all the time. However, optimizing for the worst case is very counterintuitive. So here's an example of this. Given a choice of conditions, most people will put the one that's most likely to be true first. That's just your intrinsic, as a programmer, this feels efficient. The one that's true 99% of the time, we'll put that one first, so that there's no point first checking the one that's very rarely true. However, this is a bad worst case optimization, because the worst case path will always go through the expensive calculation, which means if you put it second, the worst case path will always involve checking the likely condition first, which is extra time that's adding to that worst case execution time. So what you need to do optimizing for the worst case is put the slowest outcome first, regardless of how likely that is to happen. Another question we get from our customers regularly is, how does multicore factor into this equation in terms of timing analysis? The answer is that RapiTime in its traditional single core configuration will help you understand the relationship between the inputs to your system and its timing behavior. In a multi-core system, exactly the same thing applies. You still need to understand the relationship between your inputs and the timing analysis behavior. However, there is additional activities that need to be performed, which is you have to understand the relationship between interference from other cores and your system's timing behavior. So in addition to the RapiTime tool, we have also developed a CAS32A compliance package, which includes RapiDaemons, which are small code fragments designed to generate different types of interference, which help you with that second objective of measuring the interference from other cores and demonstrating that your interference mitigation strategies are working as expected. Finally, RVS can help you analyze handwritten code that's not part of the model. As we mentioned before, there's always some level of startup code, device drivers, or other code not part of the model that still requires measurement and testing for DO-178C. So we're now going to show you a video of what all this looks like in practice. Hello, we're now going to follow on directly from the demonstration Francois presented earlier. Here we will see how we can run the same tests on the target hardware and also get timing information. This is the RVS Project Manager. From here you can configure and run your RVS projects. However, everything I'm going to show you can also be done on the command line, making it easy to integrate RVS with an existing continuous integration system. These are exactly the same test definition files used with SCADE earlier. RapiTest can read them and generate a test harness that can be run on target. In order to do this, we use a compiler wrapper. This program lets us intercept calls to the compiler so that we can add timing instrumentation and test code before passing the modified source to the real compiler. This removes the need to make any changes to the build system. We're now going to run the tests on the target, which is an STM32F4 ARM microcontroller. The tests have completed and we're now downloading the results using a JTAG debugger. That's not the only way we can extract the data. It's possible to use serial or Ethernet or any other interface that you have for communicating with your target. RVS is now processing the test data and the timing traces in order to generate a report, which will open automatically as soon as the process completes. The first screen the user is presented with contains the test results. Here we can confirm they match the result obtained from the model. The results from individual tests can be expanded to view more detail, and we can also check the reason for any failures. Next we can see the timing analysis results. For each function we report the minimum, average, maximum, high watermark and worst case execution times. The first 5 metrics are extracted directly from the trace data. The worst case execution time, however, is calculated by examining all possible paths through the code and combining these with the measured execution times of each block of code. As you can see, the worst case execution time is higher than any execution time observed in testing. To understand why this is the case, we can compare the slowest observed path, highlighted in purple, with the predicted worst case path, highlighted in blue. When both paths are highlighted, the observed path is drawn on top of the worst case path. This allows you to quickly identify code that is on the worst case path but not on the slowest observed path. You can then add additional test cases to hit these paths, and these tests can first be run on the model before checking the correlation on the real hardware. RapiTime provides a wealth of data about your system. For each block of code, we can see its execution time profile, which shows the frequency that certain times are exceeded, as well as the distribution of execution times. Here there is a nice normal distribution of time on the left, but there are some outliers on the right that are more than twice the average execution time, and this may be cause for concern. RapiTime can also show you the order in which events occurred during the test. The invocation timeline shows when every function call occurred, as well as highlighting the maximum times. Sub-function calls are also shown in order, and we can zoom in to view more detail. We can also directly play back the execution traces, stepping through each instrumentation point as well as into and out of functions, just like a debugger. However, unlike most debuggers, we can go backwards as well as forwards, as sometimes the reason for a timing overrun was caused by the previous iteration. We can export the timing and test data from the report in a variety of different formats. Like SCADE, we offer a qualification kit for all our tools that includes and allows for a qualified export of timing and test data for submission to certification authorities. Finally, if you have any handwritten code, such as startup routines or device drivers, that is not part of the model, we can also measure the code coverage of this on host or on target using RapiCover. This concludes the process of back-to-back testing, first directly on the model and then on generated code running on the real hardware.
So, to kick us off, we've got a question from Tabani, which I think will be best going to Matt, which is, how do you account for the overhead of instrumentation in timing analysis?
Thanks, Nick. So, first of all, we engineered the RVS to be as efficient as possible in terms of where it places the instrumentation points, and we can also tune the code that is executed for each instrumentation point to make it as fast as possible. However, there is still some overhead associated with the timing instrumentation. You can remove this from the analysis if the timing, if the overhead is consistent for each instrumentation point. The other approach is that you can start removing instrumentation from the bottom of the call tree and work upwards and check that at each level the times you get for the root function is still the same. And finally, some of our customers actually leave the instrumentation code in the production software, and that way you know that you're testing exactly the same code that is going into production.
Yeah, that makes sense. Thank you very much, Matt. Another question we've had via email, probably best for Francois, this one. What do you do if the results from the target don't match the results from the model?
In fact, what we can get from the model is a worst case execution. So it's, in general, it's very pessimistic, but it's always, on the target is always lower than this. So in fact, what you will get at the model is I would say pessimistic worst time execution. Then you will refine it using, for instance, RapiTest, and you will get a more real, a more actual value with the values that you will get on the target, on the real one.
Thank you, Francois. That's helpful. We've just had a question in over the chat from Martin. Thanks for your question, Martin. For model-based testing, you usually also have expensive simulations for the environment. How does such an infrastructure integrate in the proposed methods? I'll leave that to you guys to figure out who's best to answer.
Maybe I will start. So really what we do with SCADE, the SCADE test, is really the testing of the application, only the application part. And we are stimulating the application part and not at all the environment, etc. But in addition to this, we provide a SCADE test API allowing our customers to use the tooling that we have in a more complete testing environment. I mean, if the customer wants to perform some model and code coverage in his own environment, this is fully possible, running the test that they have in a model in the loop environment, for instance. So this was my part of the answer.
Sure. Yes, I can just add to that the RVS tools can run in what we call managed or unmanaged mode. In unmanaged mode, we assume that some other system is driving the inputs and outputs to the system, and we'll simply report either the execution time or the code coverage as achieved by that software. We can also run managed tests with RapiTest, which is where RVS is now responsible for providing the inputs and checking the outputs, and RapiTest is able to stub out functions so that you can simulate sensors and other things.
Brilliant. I hope that answers your question, Martin. I've just had one that's just managed to get in through email as well, which I'll put to Matt as it's RVS focused. How does RVS see new tests that are added?
Yeah, so we can set up a task to automatically import them into RVS. We can also you can also configure a folder to look in for your tests, so any new files that are added to that folder will be picked up automatically.